Okay, hello everybody. How to describe linear spaces, lines and planes. Well, we can describe them as the image of a map or as the preimage, and sometimes one will be easier than the other. In fact, they will be the images of a linear map, a linear space, a flat space, a line, a straight line, or a plane, a flat plane. And these will be linear maps. And also the preimage of a linear map. So we're going to start with this case. Let's say I'm in the plane and I have this line. And I want to describe it as the image of a map. What I do is I just pick any vector along that line. Let's say this is the vector 4, 1. Then I have the map. Let's say v1 goes to v1 times the vector 4, 1. So this is a real number I'm thinking of, and it goes to R2. The image of this map is the set of all the outputs when I plug in every possible input. And that means I take every possible scalar multiple of that vector and gives me the line. Okay, so I think you understand this at this point. And it's sort of intuitive, which is nice. Now notice this line went through the origin. As the preimage of a linear map, we would think about I'll do this in orange, the normal vector. We'd pick any normal vector to that line at 90 degrees, and we would say that we'd send R2 to R by taking a point of R2 and sending it to n dot, okay, that point. So what's the dot product? It would be n1x plus n2y equals 0. And because we have equals 0, we didn't shift the line, and so our line goes through the origin. And it's all the points in the plane, like this purple vector, that are orthogonal to our normal vector, n. So in this case, we could even choose a specific normal vector. For example, if n were -1, 4, this would work. Here n is -1, 4, and this is the equation, we'd say it's the implicit equation of this exact line. Okay? And it's the preimage because it's the preimage of 0. It's all the inputs that get sent to 0 by, and maybe, to write a map, I don't have usually an equation like that. So then the line is the preimage of 0. Preimage of 0 under this map. Or we could say all solutions to the equation negative x plus 4y equals 0. So these are two ways to say the same thing. Okay. Let's go up to planes. Let's say I have a plane in 3-dimensional space, and let's say it goes through the origin. My plane passes through the origin. There it is. And now the same thing is on that plane, on the line I chose a vector, so on that plane I choose two different vectors. Okay? And let's say one of them was the vector 2, 3, 2. The other was the vector -1, -2, 5. Okay? Then I will send a map. Well, this plane is 2-dimensional. So my map will send 2 space into 3 space. And the image will be the plane inside of 3 space. What do I do? I'll take v1, v2, two real numbers, and send them to v1 times the first vector plus v2 times the second vector. A linear combination. This is a linear map. And the image is the plane. So the image of a linear map is a linear space. Either it could be a line, it could be a plane, it could be a higher dimensional version. The image of a linear map is a linear space passing through the origin. Okay, because if I plug in 0, 0, I'm going to get the 0 vector. over here. Okay, and as the preimage, we would then choose some kind of normal. We could take the cross product of those two and get a normal vector. It's at 90 degrees. It's hard to draw, but it's at 90 degrees. And then let's say that normal vector was, well, we could take the cross product of these and get an actual normal vector, but since I don't know it, I'll call it n1, n2, n3. I could find out what these numbers are by taking the cross product. And then I could say, well, it's all solutions to the equation. Well, now I need three variables. n1x plus n2y plus n3z equals 0. In other words, it's the preimage of the map that sends x, y, z. It's all the solutions, the preimage of this map that sends it to, and now I don't need the equation. You see, this is just two ways of saying the same thing. Oh, not that. There we go. So this is a map from R3 to R, and its solutions, or its preimage of 0, all the things that give 0, is this plane. Okay. So that's basically it. Now there's one more thing. What if we want to shift our line off the origin? So what if we wanted this, not this line, but this red line over here, parallel? Well, then we just need a point on that line. And what we do is we just take our formula and we start it. We start it at that point. Let's say this is the point, -5, 2. Then we start at -5, 2, and we add the linear combinations of vectors in that line. And so this is just a shift. And the map isn't quite linear anymore. This is the linear part of the map, and this is the shift. Now the image of this map is the red line. Okay. Over in the other side, we would say equals some number, like 5. And so that would give the shift. We'd have to figure out what that number is, and we covered that in previous videos. But then we would say, it's not the preimage of 0, it's the preimage of, maybe it's 17. Or maybe it's the preimage of -8. We'd need to figure out what number to shift our line from the blue to the red. Same thing with the plane. What if we shifted the plane? We wanted to shift it over here. Oh, that doesn't look parallel. It's the same tilted plane, but instead of passing through the origin, we shift it to pass through a different point. So we just pick any point on that plane, and then we just take our formula, and the linear piece, we move it over, and we put some point on the line that we want it to shift through, and we add the linear piece. So now this map here is not quite linear anymore. It's got a shift. But its image, the image of this map, is this flat linear space shifted off the origin. And now, instead of the preimage of 0, we'd have to figure out the preimage of some number. And in a previous video, we saw how to find that number. And we can also describe this red plane that's shifted off the origin as solutions to an equation, or the preimage of that point under this map. Okay, that's it. You know how to do this. The formulas might be scary, but it's just linear combinations of vectors that move you in that linear space. Right? This purple vector moves you along the line. These purple vectors move you inside of that plane. And then if we want to shift, we have to figure out a point on that shifted line. Oftentimes we will know that point already. And if we want to shift over here, we need to figure out what number to put on the right-hand side of our equation. And this is how you describe linear spaces. In the next video, we'll take curves, and we'll already have a point on the curve, and we'll want to describe that linear space that best approximates the curve. In other videos, we'll have a surface, and we'll also have a point on that surface somewhere, and we want to describe the linear space the tangent plane that best approximates the surface at that point. And this is how we do it.